Welcome back to the Fullerton College Pre-Press class. This is your instructor, Ben Hewitt. Where we last left our hero, we were talking about additive color and how additive color starts with darkness, and then you start adding different wavelengths and types of light energy. Remembering that red, green, and blue are considered primary colors that you can mix any other color with in light, as we have a red, a green, and a blue sensor in our eyes, actually many of each, but just simplifying it. We have parts of our eyes that see red light, parts that see blue light, and parts that see green light. All the colors that we experience come from different ratios of those three parts of our eyes, also the fourth part of our eye, the one that does light to dark, being activated or tickled, however you want to call it, receiving light and saying, hey, I sense this. So sensor data in our vision system tells us how much of each of those we're seeing, and the information comes out as a, pun intended, color-coded graph that we see, or that our brain tells us we are seeing. So that is additive color. Today we're going to talk a bit more about subtractive color. Subtractive color is kind of not the opposite, but let's go with inverse of that. And in fact, the color mixing is kind of opposite. One of these days, if I get good at animation, I'll animate a really clever rotating color wheel to show how this works. But my animation skills are not even up to that task, which is depressing. But I'm not an animator, am I? Anyways, so subtractive color starts with white background because white contains all the colors of light. Once again, the whole Saruman, the white turning into Saruman, the many-colored, by the end of the book series, spoiler alert, Saruman stops being Saruman the white at some point and becomes Saruman the multicolored. At this point, you've not read books from the 70s. It's on you that you don't know this. But anyways, because light is made up of all the colors, then it stands to reason, and is actually how it works, that you can remove some of that color and see only the parts that you want to. So if you are seeing a paper that looks white to you, and neutrally white, not just, we'll talk about that too later. If you're looking at a white paper and it looks neutral and it looks white to you, that's because your eyes are seeing an equal amount of red, green, and blue light, and enough of it that your rods are telling you that it's bright enough to be white. Otherwise, you're seeing gray or black. So printing process, as well as anything else using ink or paint or colors that we work with, are all using subtractive color. Here's the subtractive color wheel. In the subtractive color wheel, your background is white because you're starting with, hopefully, full spectrum light, and you're simply removing the parts that you're not interested in seeing. So if you're talking about this in other methods, let's compare these through more heavy-handed instructor analogies here. Let's talk about this in terms of sculpture. So you kind of, hopefully this will help you. I like things in my hands. It helps me think and organize to be holding something. Pens always work. But anyways, in sculpting, if you're talking like additive color, then your sculpture is more like a Lego sculpture where you are building out of pieces and you're stacking them up. Or if we want to go a bit more towards the other ones, let's say it's like building a sandcastle. You start with nothing and you add on top of it until you build that sandcastle. But subtractive color is more like sculpting by carving out of a block of stone. You start out with a solid block of stone and you remove the parts you don't want until, hey, look, it's Venus de Milo. So anyways, it's all about removing the parts you don't want to see and only leaving the parts that you do want. So it's carving as opposed to assembling. It's milling something out of a solid piece of light rather than assembling it out of bits of other lights. So that's going to mean a couple things for us. One of them is, hopefully this is logical and obvious, but in case it's not, let's spell this out. If you are starting with white light and removing parts to leave what you want, step one is to make sure that you're starting with everything. Your lighting, the whiteness of your paper is extremely important. And I don't mean to sound weird by saying this, but it's because you cannot achieve all the colors if you don't start out with a good, again, neutral, white, bright white. If your paper is a little bit yellow or a little bit gray or a little bit blue, Those are the three kind of directions you'll often find white paper being when it's not pure. That means that you're not going to be able to print all the colors you thought you were going to be able to. Some of the colors will not be able to be achieved because in order for subtractive color to work, you have to start with all the colors you want already reflecting off that paper. And if it's not reflecting all of them, then there are some that you're not going to be able to do. Because remember, with subtractive color, I know when you think about mixing inks and mixing paint, but take that out of your brain for a minute and think about the fact that you are using those things as scalpels, as knives, as chisels to remove stuff you don't want. Even when you're painting a picture with watercolors or oil paints, although you think about building up layers of color, that's how I used to teach painting when I worked for a hobby shop many years ago. What you're really doing is you're taking the light that reflects off of that canvas and you're removing the parts that you don't want the viewer to see. When you're putting on that red paint, what you're really doing is saying, I don't want you to see that green or that blue light anymore. So this material that I'm smearing on this canvas is removing green light and blue light so that only red shows. So that means that the brighter and the cleaner the white is of your substrate, the clearer you are going to get your print. The better color, the more colors you can reproduce. Here's the money shot from this whole course. If you are only going to learn one thing this semester, I'd still prefer it be bleed. And we're going to talk more and more about that. Don't worry. But if you're going to learn two things this semester, memorize this image. Actually, don't memorize. Understand what this image here is showing you. This is by far the most important image in the entire pre-press combined course. This is the same blue ink printed on, to count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. I actually kind of lost interest in counting. 15 or so different papers. Some of them are coated, some of them are uncoated. You can kind of see how it acts on the different papers. This is by no means a comprehensive list of how ink acts on paper. But the point, the message I want you to get is the paper matters. In 4-color printing, cyan, magenta, yellow, black, paper is color number 5. It's the 5th color in 4-color printing. The color of your paper will affect everything. And now it's obvious if you take it to extremes. If you think like you're printing on one of those old, Astro Bright, whatever you call it, rocket red colored papers where it's super bright, almost fluorescent red, and these are 1-color flyers with red background, but you try to print color on that, you already know what's going to happen if you try to print normal coloring images on colored paper. Because you're not playing with a full deck, so to speak. You don't have all the colors represented. If your paper is bright red, then your paper is already removing the green and the blue. And if you try to print with colors that are going to remove green and blue, you try to print colors that show green and blue, what you're really going to end up with is something closer to black, because you're going to be removing all the light. Because if it's red, it's already removing green and blue. So anyways, here you go. You can see different effects. Coated versus uncoated also changes things. Coated paper, the ink does not soak in as much, so it's brighter. It doesn't mix, so to speak, with the color of the paper. If you print on uncoated, you're more likely to get a pastel result because the paper itself will show more as it absorbs the ink and more of its own color comes through. Those brown ones are craft paper. I really enjoy these for special projects, by the way. And they're kind of unbleached or raw, or you can still see the color of the wood that it once was coming through. Anyways, the whole point here is the same ink will act differently on different paper, so you cannot ignore the paper. The paper is not a gimme. It's not this standard thing that's always going to be white. You have to pick it carefully for what you're doing. In fact, allow me to help you to judge paper better. The uninitiated, and many clients I've worked with, and even myself sometimes, I often fall into it. The first inclination when you find a piece of paper is to feel how thick it is, and you judge its value based off of its thickness. People will hold up a piece of paper and say, this is cheap paper because it's kind of thin. And while that is true, a lot of cheap paper is thin, that doesn't account for some extremely high-end thin paper, which exists for things like, again, Bibles and what do you call them? Dictionaries and other thick reference volumes that have multiple thousands of pages, and that thin leafy paper, well, that allows you to have those pages without the book weighing 2.5 tons. And if that paper still doesn't show the ink on the other side, wow, that is some good paper. I'm just saying that the thickness is not it. In fact, If I were to judge paper, and actually I do, it's literally my job to do that, I would actually say that the whiteness of the paper is something you want to evaluate, because the whiteness and the ink holdout, which is how much it absorbs ink or doesn't, how well does it resist ink soakage, those two factors are the ones that determine how good a reproduction you're going to get on its surface. So if you want a good bright white that does not soak in ink, you're going to get the cleanest possible prints with the brightest possible colors on top. And again, we're not looking for whiteness because whiteness is what we need or what we want. We're looking for whiteness because that will help us achieve all the other colors. Without a pure white paper, you cannot print all the colors of your gamut. You will lose some, or the gamuts of off-white paper. This is also where I'm going to have to warn you about something that I don't believe is in this. Scoot, scoot, back, back, which is the dangers of the OBA, optical brightening additive. There are papers that will cheat human perception to appear brighter than they actually are. We've determined that when people see a bright light, if it's slightly bluish, we think it's even brighter than it is, because that's just something that we sense. An abundance of blue light helps us think that a light is brighter. So if your paper has a little bit of a fluorescent blueness to it, it will appear whiter than white. And it will look like the most perfect paper ever until you print on it and none of your colors come out correct. You're like, what is going on? Why isn't this working? Well, the answer is it isn't actually what you thought it was. It was cheating you. So inks filter the surround. The inks will remove, again, part of what we don't want to see. We can reproduce quite a bit of color by using our subtractive primaries, which are cyan, magenta, and yellow. Red, yellow, and blue that you learned in kindergarten is only sort of true. Cyan, magenta, and yellow actually give you a wider range of possibilities. The truth of this has to do with both the fact that they are really the primaries, but also have to do with pigment issues. You can't get a pure enough blue or a pure enough red pigment out of the materials available to us on this planet. So any red ink that you use or red paint is going to be either slightly orange or slightly purple. And any blue that you use is going to be slightly green or slightly purple. And if you use a slightly purple blue and a slightly orange red to make a purple, instead of getting a purple, you're going to get brown, because the greenish part of the blue and the yellowish part of the red are going to come in there and make it so you're seeing all three primaries and make it so it's brown instead of properly the purple you were aiming for. Purple is notoriously hard to do. One of the greatest projects I ever had to do in my undergraduate work when I was learning painting as part of my visual arts degree was I had a painting teacher who required us to paint a color circle, just a color wheel, using only red, yellow, and blue paint, the way we all thought it's supposed to work. And everyone came in, and depending on which red or blue paint you had, and sometimes which yellow can actually be fairly pure, thankfully, but depending on which red or blue brand of paint you were using, you were going to have problems in the purple. Because unless you are, or in the orange or in the green kind of areas, because if you had it leaning slightly one of those directions, when you mix them with each other, you get the muddier, browner, grayer, trichromatic, which is a word that's going to haunt us later, color, rather than the pure secondary color you were aiming for. But the cyan, magenta, and yellow are perfect filters for removing red, green, and blue light, respectively. Here's a diagram, and there's a second video I put up for this as well that you can see, showing how this works. And we'll go through this again in another video because I'm starting to run short on time, but we'll do this once here, and then we'll pause and reconvene. So white light bounces off your paper and reaches your eye. If the paper is white, the red, green, and blue elements of that white light all bounce off the paper and come back to your eye, and you see all of it. And if your eyeball sees equal red, green, and blue, your eyeball says, and I do mean your whole vision system, your eye and your brain, your optic nerves, and all that, says, I see white. Now, if there's a cyan filter on the paper, an ink that's cyan colored, that white light, the red, green, and blue, hits the paper. The red light is unable to escape. It gets filtered out. It gets absorbed by the cyan ink on the paper, and then your eye only gets the green and the blue. And the green and the blue look cyan to us because there's no red in it. All right, I'm going to stop here. We'll come back and look at this and more of these. And don't forget to check out the related video, which shows a more animated diagram of this. Thanks for listening. I'll talk to you guys soon.